Welcome to the fourth lesson in our trigonometry unit. This lesson is going to talk about the special angles. And our goal here is that we can state the exact values of sine, cosine, and tangent of the special angles 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and their multiples, and use them to determine the exact values for the unknown quantities. So, first of all, we're going to start with a 30, 60, 90 degree angle triangle. So I have a nice little picture here. I've labeled the angles appropriately. And what we're going to do here is I'm going to get you to use your calculator to evaluate the sine of 30 degrees. Make sure your calculator's in degree mode, of course. And when you evaluate that, you're going to notice that you get a nice terminating decimal value of 0.5. So the sine of 30 degrees is equal to 0.5. Now, if we think about what sine means, let's write this down for a second. The sine of 30 degrees is equal to 0.5. 0.5 really is the same thing as 1/2. 50 cents is a half of a dollar, so that's 1/2. And when we talk about the sine really is the ratio of the opposite compared to the hypotenuse. So, if we look at our triangle here, opposite to the 30 degree angle would be this side. So I'm going to label that as a 1, and then my hypotenuse is over here, and I'm going to label it as 2 units. So the opposite side is half as much as the hypotenuse, or you can think of the hypotenuse being double the length of the opposite side. All right, now the second step here is use the Pythagorean theorem to calculate the exact length of the third side. I just realized I have a typo there. Let's see if I can fix that. So you use the Pythagorean theorem, calculate the length of this third side that we don't know yet, the one across from our 60 degree angle. Okay, so if you've done that, this is a short side that we're trying to find. So I know that my short side, I'll just call that b squared, would equal my hypotenuse squared minus the other short side squared. So it's the rearrangement of that c squared equals a squared plus b squared. So 4 take away 1 would equal 3. That's a takeaway sign there. So b squared is equal to 3, and since b is just a length, when I take the square root, I only need the positive square root of that, and I get that that exact length is the square root of 3, whatever that is equal to. All right, now what we have, in fact, this will always be true, regardless of how big or how small that 30, 60, 90 degree angle triangle is. The ratio of the sides are always in the form 1 to root 3 to 2. All right, so I'm just going to summarize that here as a sentence. Okay, so a 30, 60, 90 degree angle triangle will always have its sides in the ratio of 1 to root 3 to 2. The 1 is the shortest side, so it's always the one across from the 30 degree angle, and the 2 is the longest of those 3, and that always has to be your hypotenuse across from your largest angle, which is the 90 degree angle. All right, let's take a look at the 45, 45, 90 degree angle triangle. This triangle is isosceles. Because the 45 angle here and the 45 angle here are equivalent, it means that the sides across from those angles are equal in length. So we're going to let the short sides of that triangle be 1 unit long each. Okay, so this will be a 1 unit and this will be 1 unit long. Now what we're going to do is just use the Pythagorean theorem to determine the length of the hypotenuse. So this time we are finding the hypotenuse length, so I'll call that c for now. C squared would equal the sum of the squares of the lengths of the 2 shorter sides. So 1 squared is 1, and we're adding another 1 squared, which is 1, so that gives us a 2 overall. Square root that to get c, and again it's just a length, so we're only caring about the positive square root. That hypotenuse is root 2 units long. So in a 45, 45, 90 degree angle triangle, the side lengths are always in the ratio of 1 to 1 to square root 2. Okay, so the 45, 45, 90 degree triangle will always have its sides in the ratio of 1 to 1 to square root 2. And again, the square root of 2 is bigger than 1. It's going to be the length of our hypotenuse, and then the 1s are our shorter sides. So the hypotenuse is the root 2, hypotenuse. And that didn't come out very well, but just remember that that says hypotenuse there. Sometimes you'll also see that ratio instead as root 2 to the root 2, so the two shorter sides are the square root of 2, square root of 2. If you apply the Pythagorean theorem to that, that makes the hypotenuse 2 units long. But in the end, the ratios will be the same. So if I want to state my trig ratios based on a 45-degree angle, looking at that, we can say that the sine of 45 degrees is going to automatically be equal to opposite over hypotenuse, and the opposite is 1 over the square root of 2. Or you might see that written as root 2 over 2, just depending on which version they're using. But in the end, if you do the division, you get the same answer. The cosine of 45 degrees is also 1 over root 2. And then the tangent of 45 degrees is going to equal, tan of 45 is opposite over adjacent, which is 1 over 1, which is just plain old 1. If I slide back up to my 30, 60, 90, we could look at the sine of 30 degrees. That we already know is 1 over 2. The cosine of 30 degrees, so I'm sliding back up to the first example here. The cosine of 30 degrees would be adjacent, which is root 3 over 2. And the tan of 30 degrees would be, tan of 30 degrees is going to equal opposite, which is 1 over adjacent, which is root 3. So these are the exact values of the 30-degree angle and the 45-degree angle. Now I can also use this 60, 30, 90-degree triangle and state my three trig ratios in terms of the angle that is the 60-degree angle. If I want the sine of 60 degrees, so the sine of 60 degrees, it's going to equal opposite, which is root 3, over hypotenuse. The cosine of 60 degrees, based on my diagram here, would be 1 over 2, adjacent over hypotenuse. And the tan of 60 degrees, tangent of 60 degrees, would be opposite, root 3, over adjacent, which is 1, and root 3 divided by 1 is just root 3. So knowing what the ratios of our special triangles are, ratios of the side lengths, is really important here. You should be able to redraw this triangle and label the sides in the ratio of 1, 2, square root 3, or for the 45, 45, 90, the 1, 1, square root 2. And then we can use that information to help us solve some problems. All right. We're going to talk about the 0 and the 90 degrees in a bit, in another lesson. Okay, take a look at this example. Use the ratios of the triangles to determine the exact values of the known side lengths, of the unknown side lengths. My apologies there. We've got a 90 degree, 60 degree angle here. That by default, angles in a triangle add to 180. That makes this little angle up at the top a 30 degree angle there. Now, we know that a 30, 60, 90 degree angle triangle will have the side lengths in the ratio of 1. 1 goes across from the smallest angle, so my 30 degree angle, the side across from it has to be 1. The 2 is the longest side, it goes with the hypotenuse, and the middle side across from the 60 degree angle is the square root of 3. 1, 2, square root 3. So what we're going to do is use that ratio to help us find the unknown side lengths. Now I know that the hypotenuse is 12 centimeters. That means I would take 2 and multiply it by 6 to get to be 12. So that's a multiplication there. 2 times 6 is what equals 12. That just means all my other sides have to be the same multiple. I would have to take the 1 and multiply by 6, and the root 3 gets multiplied by 6. So my unknown side lengths here are just 6 and 6 times the square root of 3, or 6 roots of 3. The second triangle here has a 90 degree angle, so this is my hypotenuse here. The 18 centimeters is my hypotenuse. And these two other sides are equal in length. That means the triangle is isosceles. That means this has to be 45 degrees, and this has to be 45 degrees. 180 minus this 90 leaves us with 90 degrees. That's split up evenly or equally between these two bottom angles here. All right, that means my side lengths are in the ratio of 1, 1, square root 2. All right, so now we need to come up with what to multiply the square root of 2 by to get it to equal 18. So think of it this way. Root 2 times some number, x, we don't know what that number is yet, has to equal 18. If I want to solve for x, I'm going to divide both sides by the square root of 2, and that undoes it here. And that leaves us with x being equal to 18 divided by the square root of 2. Which then means if I'm multiplying this by 18 over the square root of 2 to make it equal to my 18, then both of the other sides have to get multiplied by 18 over the square root of 2 to keep the sides in the ratio of 1, 1, square root 2. So my two equal sides here are equivalent to 18 divided by the square root of 2. All right, let's look at example 2 here. Sketch the angle of 120 degrees in standard position. Okay, so we've already talked about what standard position looks like. So I'm going to draw my Cartesian plane here. There's x, here's y. 120 degrees is 30 more than 90 degrees. So it's going to look something like that. So that's my 120 degree angle. Use the related acute angle. Oh, I got to figure that out. Well, the related acute angle is just this little guy down here. I know the whole flat line is 180 degrees. My related acute angle then would be 60 degrees because 60 plus the 120 would add up to 180 degrees. All right, so then what I have is I can construct a nice little right angle triangle here. This would look way better if I actually could use a ruler here. That means the side across from the 60 degrees would be our opposite. This is our hypotenuse, and this is the adjacent. Now, in terms of labeling our side lengths, we know that across from the 60 degrees, that's the middle, that will be the root 3. The adjacent will be across from 30 degrees, it's a 1, and this will be a 2 as my hypotenuse. Now, the only thing we have to consider here is that we are in the second quadrant. So in terms of getting to the point on our terminal arm, I would actually be going to the left 1 unit. So heading to the left by 1 unit, and then we're heading up. I'm just going to undo that there. We're heading to the left 1 unit, and then we're heading up root 3 units. So that's why I have to make this a -1, but I'm heading up, so that's a positive root 3. My hypotenuse is always going to be a positive number when I'm doing this. So my 3 primary trig ratios are as follows. We know that the sine of 120 degrees, we just look at the related acute angle as our angle kind of reference here. The opposite is root 3, and the hypotenuse is 2. So sine is positive in the second quadrant. The cosine of 120 degrees would be adjacent, which is -1, over hypotenuse, which is 2. And the tangent of 120 degrees would be opposite, root 3, over adjacent, which is -1. So that you would most likely see as -root 3. Okay, yeah, so there we are, the exact values.